Welcome to the deep dive. Today, we are cracking open the very foundation of our existence. We're doing an intensive deep dive into Earth systems.
Right. This is the stuff you might find in, say, Chapter 8 of a good environmental science book.
Exactly. It's essentially the story of the ground beneath our feet. And I promise you, it is anything but static or, boring.
That's the key takeaway, isn't it? Our mission today is really to give you the essential, high-impact knowledge on geology, plate tectonics, all of it.
The rock cycle, erosion.
Yeah, we're going to try and cut through some of that dense complexity, just focus on the key processes, maybe some surprising facts that explain how our planet is actually structured.
And how it maintains life, which is the critical part.
Exactly.
And before anyone dismisses this as, purely academic, you have to remember that these systems directly dictate human economics, our survival even.
Oh, massively. We're talking billions of dollars in real-world application.
For sure. Think about the huge agricultural output in places like California's Central Valley. That incredible fertility, it depends entirely on weathered, eroded, and then deposited rock.
That's what creates that perfect, rich topsoil. So if you understand the rock cycle, you sort of understand the wealth cycle.
Well, let's start at the source then, deep inside the planet.
Let's do it. So the Earth's crust and the very top part of the mantle, together they form what we call the lithosphere.
Right, the lithosphere. And it's not one solid shell, is it?
No, not at all. It's broken up into these massive, rigid pieces called tectonic plates. And they aren't just floating on, liquid lava. They're on a layer of worner, less rigid rock called the asthenosphere.
The asthenosphere, so it's more plastic.
That's a great way to put it. It can flow very, very slowly.
So what's driving this planetary scale traffic jam?
It's all about thermal energy. It's heat loss from the Earth's core, and that generates these slow but incredibly powerful convection currents in the mantle.
Like a slow motion pot of soup circulating heat.
Exactly like that. And when you say slow, you really mean it.
Painfully slow. We're talking speeds that are sometimes barely a centimeter a year.
The movement might be glacial, but the consequences are just massive. You see three main types of interaction at these plate boundaries. You have divergent boundaries.
Yeah, they pull apart.
Right, creating new seafloor.
Yeah.
Then you have transform boundaries.
Yeah.
That's where plates slide horizontally past each other. That's where you get your major fault system.
And of course, the most dramatic one.
The convergent boundary.
Oh.
This is where plates collide.
Right.
And what happens next? Well, it really matters what kind of plates are colliding.
Okay, so you have two main types, right? Oceanic and continental.
Exactly. And oceanic plates, because they're full of water, they're much denser. I like to think of them as the wet towel of the lithosphere. They're just heavier.
A wet towel. I like that, so they always go under.
They always slide underneath the less dense continental plates. That process is called subduction.
Subduction. And that's where things get really interesting.
Oh, yeah. Because when that oceanic plate gets dragged down, it carries a vast amount of water with it. That water lowers the melting point of the mantle rock around it, which generates magma.
And that magma has to go somewhere.
It rises. And it leads to these explosive, devastating volcanic chains like the ones that ring the Pacific.
The Ring of Fire.
The famous Ring of Fire.
So whether they're pulling apart, scraping past, or just colliding head-on, these boundaries are the high-stress zones.
That's where we see the volcanoes and, of course, the earthquakes.
Right. Earthquakes happen along fault zones, these visible cracks in the plate. Like the San Andreas Fault is a perfect example.
It is. That's the Pacific plate just grinding its way north against the North American plate.
And when that rock finally fractures under all that stress, the initial break deep in the earth, that's the focus, right?
That's the focus. The epicenter is just the point on the surface directly above it. That's the spot we always hear about in the news.
And the scale we use to measure them, the Richter scale, I think a lot of people misunderstand that. It's not a linear scale.
No, it's logarithmic.
Yeah.
It's base 10. You hear that a magnitude 7 is stronger than a 6, but that doesn't really capture it.
It doesn't at all.
A magnitude 7 earthquake releases roughly 32 times the energy of a magnitude 6.
32 times? That's a massive escalation.
It's the difference between maybe a broken window and, total structural failure across an entire city. Understanding that logarithmic scale is it's crucial.
Okay, so that puts the tectonics into perspective. But moving away from those boundary zones, there's another feature to talk about.
Hot spots.
Hot spots.
Yeah, these are plumes of magma rising from deep within the mantle. And the key detail, the most important thing to remember, is that they are stationary.
They don't move with the plates.
Exactly. The plate slides over the hotspot.
Which is how you get a chain of volcanoes. This explains the Hawaiian Islands perfectly.
It does. The Big Island is currently sitting right on top of the hotspot, so it's the active one. It's still growing.
Mhm.
The islands to the northwest, they're dormant because they've slowly moved off that heat source.
And this isn't just an ocean thing either. Yellowstone is a hot spot, right?
The Yellowstone caldera, yep. It's the result of the North American continental plate moving over a fixed hotspot. A powerful reminder that our continents are always in motion.
Always. Okay, let's transition from the dynamic core to the actual material the plates are made of. This brings us to the planet's perpetual recycling program.
The rocks and minerals.
Rocks and minerals, and we have to get the terminology right here, or we'll have geologists writing in.
Ah, yes. They're minerals, not rocks.
Exactly. So what's the difference?
A mineral is a naturally occurring solid chemical substance. It has a highly uniform, often crystalline structure. Think quartz, hematite, things like that.
Okay, and a rock.
A rock is simply an aggregate. It's a collection of one or more of those minerals all smashed or melded together.
And these aggregates are always moving through the rock cycle.
It's a continuous flow. Deep underground material is magma. Once it erupts onto the surface, we call it lava.
And these materials are transformed through melting, cooling, intense heat, pressure.
Or by being compressed into sediment. This cycle creates the three fundamental rock types. First up is igneous rock.
Formed from cooling magma or lava.
Yep. And the speed that it cools determines its texture.
So if the lava cools really fast on the surface, that's extrusive. The minerals don't have time to form big crystals.
You get fine-grained rock, like obsidian.
But if it cools very, very slowly, deep underground.
That's intrusive. You get coarse-grained, large crystal rock, like granite, which means that granite countertop in your kitchen is literally the slow-cooked, deep material of the earth.
That's a cool thought. Okay, so type number 2.
Metamorphic rock. The name literally means changed form. This is what you get when any pre-existing rock is subjected to immense heat and pressure.
So it doesn't fully melt, just gets squeezed and cooked.
Precisely. It happens near subduction zones or deep inside mountain ranges. This is how you get marble, slate, gneiss. They're incredibly tough and dense.
Which is why we use them for durable building materials. Makes sense. And finally, the third type.
Sedimentary rock. This is the rock of layers. It forms when sediments, sand, mud, gravel, shells, even huge amounts of organic matter are compressed and cemented together over time.
The Grand Canyon is the ultimate poster child for this, right?
Absolutely. Millions of years of deposition and compression, all laid out for you to see.
And you could argue this is the most relevant rock to our survival in the short term.
I would agree. Not only is this where we find fossils, but critically, the organic matter that gets trapped in these layers. Well, over geologic time, that's what creates our fossil fuels.
And there's another crucial link here to life support, right? Something about phosphorus.
Yes. The rock cycle is the primary slow-release mechanism for phosphorus. It's an essential nutrient for all life, especially plants. It's stored in certain rocks and released slowly through weathering.
So if the rock cycle stops...
The nutrient cycle eventually fails. Simple as that.
That's a fascinating connection. So the rock cycle is the planetary engine, but the surface itself is sculpted by what you call the WED trio.
The WED trio.
Yeah.
Weathering, erosion, and deposition.
Okay, breaking down weathering.
Weathering is just the breaking down of rock and material in place. It can be physical, like water freezing in a crack and expanding, busting the rock apart.
Or it can be chemical.
Right, like the effect of mild acids in rain that can dissolve limestone and create massive cave systems over time.
Okay, so once the rock is broken down, then comes erosion.
Erosion is the physical removal and movement of that broken material, the sediment. This is the transportation part. Wind-blowing sand, or much more powerfully, a river-washing silt downstream.
And deposition is the final step.
It's the inevitable third step, where all that sediment accumulates. Think of river deltas where the flow slows down and just drops its entire load. This combination, WED, is what builds the basis of our soil.
Soil. It's not just dirt, it's this complex living mixture of mineral particles, the weathered rock and organic material.
And it's stratified. It has layers, which we call horizons. They tell the story of the soil's history.
And we define these horizons from the top down. So the O horizon is on top.
O for organic. That's mostly decomposing leaves and detritus. Below that, you have the A horizon, or topsoil. That's the most biologically active layer where most plant roots are.
Then you get to the B horizon, the subsoil, where minerals have washed down.
Then the C horizon, which is the parent material weathered rock fragments. And finally, you hit the R horizon, bedrock, solid rock.
And when we talk about soil quality, we're really looking at texture, right? The ratio of sand, silt, and clay.
That's where the soil triangle comes in. You need to get that balance right. And the ideal mix for agriculture is something called loam.
Loam is the Goldilocks zone.
It really is. If you have too much sand, water drains too fast.
Mhm.
Too much clay, and the water's held too tightly, it gets saturated and chokes the roots.
So loam provides that perfect balance of aeration and moisture.
Exactly. And this leads us to the final major process that shapes our surface environments: ecological succession.
How ecosystems recover and establish themselves over time.
We break it down into two main types.
First is primary succession.
Primary succession starts from absolute scratch. Bare rock, no soil at all. Think of land after a glacier retreats, or a brand new volcanic island.
And this is agonizingly slow.
Oh, incredibly slow. It can take tens of thousands, maybe even 100,000 years. You need pioneer species like lichens to grow on the rock and chemically break it down to create the very first particles of soil.
But then you have secondary succession, which is much faster.
So much faster because the soil is already there. This happens after a big disturbance like a forest fire, a flood, or when farmland is abandoned.
So because the seed bank and the nutrients are already in the ground, recovery is measured in decades or centuries, not millennia.
Right, and that distinction is critical because so much of the environmental damage we do today, like clearing forests, it starts a secondary succession process. We see the recovery, but we have to remember the land is always trying to return to a more stable state.
That was a really comprehensive journey. We started with convection currents in the planet's molten interior, went through the deep time of the rock cycle,
That generates our building materials and nutrients.
and then finished at the surface processes that create the very soil we rely on for everything.
And the connection to our carrying capacity is just inescapable. These systems, like the slow release of phosphorus from rocks or the ability of soil to regenerate, they are constantly under pressure from us.
The concept of biospheric degradation.
Exactly. Every time human infrastructure expands, whether it's new housing or a data center, we take land out of productive ecological use. We reduce the overall natural capacity of the Earth to support us.
And it always comes back to the timeline, doesn't it? Geological processes, mountain building, mass extinctions. They're measured in epochs, millions of years.
Yeah.
The 5 previous mass extinctions played out over these vast stretches of time.
Which gave life time to slowly adapt and rebound. We, however, are now in what scientists widely call the 6th mass extinction.
And it's anthropogenic, human-caused.
It is. And while the loss of a species, maybe just a rare fern in a remote New Zealand valley, can seem slow and easy to ignore day to day, the underlying drivers are moving at a phenomenal speed, geologically speaking.
So here is the provocative thought we want to leave you with. If the deep fundamental systems of the earth plate tectonics, rock weathering operate on timescales measured in millions of years, how should we react when we see changes that are, by comparison, instantaneous?
Specifically, the dramatic exponential rise in atmospheric CO2, clearly documented by the Keeling curve, happening entirely within a single human lifetime. What does that tell us about the unprecedented speed of the change we are now driving?